guys. So we are going to continue to look at graphs today, but today we're going to focus more on all the characteristics that we've looked at this year. We're also going to review piecewise functions, and that'll also give us a little bit more graphing review. So we're going to start with all those characteristics. These are things we've done all year long, over and over and over again, that hopefully by now are going to be pretty easy for you. So we're going to start with domain and range. So if you remember domain, we look left to right. We're going to write these in interval notation. So the farthest left x value on this graph would be this point right here. Since it's an open circle at -4, we're going to use a parenthesis. Then if we look, there is nothing on this graph that is skipped. There's no open circles, so this is going to continue to infinity. All right, then range of this graph, we look bottom to top. Okay, the lowest y value on this graph is down here at -2. It's not an open circle, it's a filled in circle there, so we're going to go ahead and put a bracket. Then as we continue up, okay, looking at all the y values, yes, there's an open circle there, but there's also a filled in circle there. So that point is still included in our range. So we don't need to do anything about that when we write our range. Our range is just from -2 to infinity. All right, then we've talked about intervals where a graph is doing something. So the intervals where this graph is decreasing. Decreasing, we look left to right, and as the y values are getting smaller. Now, even though we're talking about what the y values are doing, anytime we list an interval, we're listing the x values where that's happening. So this graph is decreasing from -4 to -2, and it's decreasing from 0 to, let's see, what is that, 3. Now, in terms of the parentheses and brackets, okay, there can be some differences there, really honestly depending on the class that you're in. For the sake of this class, we're using parentheses. In some future classes, you may use brackets. It really just depends on the notation that your teacher prefers. Some professors like parentheses, some like brackets. It depends on the specific definition that you're operating with. In this class, we just always use parentheses. All right, now increasing intervals. Again, looking left to right as our y values are getting bigger. But to list the intervals, we're listing the x values where that's happening. So this is increasing from -2 to 0, and it's increasing from 3 to infinity. All right, other things we talked about for intervals were positive and negative. Positive intervals is when your y values are above the x-axis. So I'm going to go ahead and highlight where this graph is positive. Okay, so those are my positive intervals. But again, since we're talking about an interval, we're still listing the x values where that's happening. Now, parentheses and brackets on these are pretty clearly defined. Okay, it has to be exact. If you put a bracket, it means that x value has a positive y value. So where this starts is -4. Okay, -4 is not defined, so I can't put a bracket there. It needs to be a parenthesis. Then this keeps going. We can't just say it goes until 2, because at -2, it's not positive, it's 0. So I need to put that in consideration. Then this graph picks back up and is positive again at 5. And it stays positive for the entire duration. So all of these were parentheses. But if this circle were filled in, then I would have a bracket at -4, because at that point, -4 would have a positive value. Now in this case, it's not filled in, because -4 is not actually defined. All right, then we're going to talk about where it's negative. So that's going to be this part that is colored in blue. So again, we're listing the x values where that's happening. So the x values where that's happening is from 2 to 5. All right, next one, evaluating f of -2. So that means when x is -2, what does y equal? So f of -2. So when x is -2, there's the point on my graph. So if x is -2, y is 0. Going the opposite way, when f of x is -2. So when y is -2. And this could have more than one answer for a function. In this case, it only has one. So the x value where that happens is at 3. And again, there could have been more than one. In this case, that just happened to be it. All right, next one, average rate of change. So average rate of change on the interval -2 to 3. So again, interval tells you that those are x values. So from the x value of -2 until the x value of 3 on your graph, what is the average rate of change? Another way of asking that is basically, what's the slope from one point to the other? So you can just find this on the graph. What's your rise over run? Well, first of all, we know it's negative. All right, we've gone down 2, and we've gone over 5. So the average rate of change on that interval is just the slope on that interval. So the slope from the x value of -2 until the x value of 3. All right, then the last thing we talked about were our relative extrema. So our mins and our maxes and our absolute and global mins and maxes. So remember, each of these had another word. Okay, relative, you also could have seen the word local. Absolute, you also saw the word global. So the relative min or max is the lowest point relative to the points around it. All right, so that would be, for example, this point down here. It's not the lowest point in the entire graph, but it is the lowest point relative to all those points to the left and right of it. So that point right there is a relative minimum. Now, really the way we list it, the value of the minimum is the y-coordinate. Where it is the x-coordinate. So the actual minimum is 0. Okay? It happens when x equals -2. Another relative minimum is down here. So -2 is also a relative minimum, and that happens when x equals 3. All right, a relative maximum. That would be this point up here. So that is, again, relative to all the points around it, the highest point. It's not the highest point on the graph, but it's highest of the points nearest it. So 2 is a relative maximum, and that happens when x equals 0. Now, this open circle here is not a relative maximum. In fact, if it were filled in, it still wouldn't be a relative maximum because there's nothing to relate it to on the left side. So at that point, it is possible for it to be an absolute min or max, but it's not going to be relative because, again, we can't really compare it to anything on both sides. All right, so then finally looking at absolute or global mins or maxes. So in this case, this graph does have an absolute or global min or max. That point right there is the lowest point on the entire graph. So this graph does have an absolute minimum. The value of that minimum is -2. It happens when x equals 3. This graph does not have an absolute maximum, though, because this graph continues all the way to infinity. Now, if that arrow wasn't there and that graph stopped, then yes, this graph would have an absolute maximum. But this one doesn't stop. This one keeps going. All right, so the only other vocab piece, well, there's 2 more vocab pieces that weren't listed on here. One of them was end behavior. I didn't relist it because, again, we've done that so many times this year for all these functions. And for this particular case, there's only one side end behavior because the left side doesn't really approach anything. But just to review, as x approaches positive infinity, y is approaching positive infinity. Now, x doesn't approach negative infinity on this graph. If you want to, you could say as x approaches negative, is that 4? And you could say as x approaches -4 from the right side, you could say that y approaches 3. Okay, but again, we don't need to do that. You'll get into that in your pre-calc class and in calculus when we start talking about those one-sided things. All right, so then the next thing we're going to do is review piecewise functions. So piecewise functions are really good because they really combine everything we've done so far this year. We're also going to look at discontinuities. That's the other piece, the vocab piece that wasn't listed previously because that graph we just did didn't have any discontinuities. So in order to graph a piecewise function, you remember the way this works, you have a particular function for a particular domain. So this first one, all right, that's a parabola. It's been shifted left 2 and up 1. we're only graphing when x is less than negative 2. Now, there's a lot of different ways you could do this. If you want to just graph the function and erase half of it, that's fine. What I usually do is I usually take this point and I start by plugging that point in. So if I take negative 2 and plug it in, then I'm going to get 1. Because it's less than, not less than or equal to, negative 2, 1 is an open circle. Then, because it's x is less than, I'm only going to graph to the left of this point. Well, if you're not familiar with what that parent function looks like, you can plug in negative 3 and negative 4 to get an idea. So if I plug in negative 3, that would give me negative 1 squared, which is 1. 1 plus 1 is 2. If I plug in negative 4, negative 4 plus 2 is negative 2. Negative 2 squared is 4. 4 plus 1 is 5. Okay, also, if I just knew what this graph looked like, I would know, hey, that's a parabola, and that's the vertex. All right, now let's graph the next piece. When x is greater than negative 2, I'm graphing the line 1/2 x minus 1. So again, even though I know 1/2 x minus 1 is going to have a y-intercept of negative 1 and a slope of 1/2, I'm still going to go ahead and plug in negative 2 just so I know exactly where this graph is starting in case it's like some ugly fraction. In this case, it's not, but just in case it were. So if I plug in negative 2, that gives me negative 1 minus 1, which is negative 2. And then again, it's going to be an open circle. And then this graph is just going to continue on that slope. All right, now looking at the next one, same idea, just 3 intervals this time. So x minus 2 when x is less than negative 1. Let's plug in negative 1. So negative 1, negative 3 is going to be an open circle. Everything to the left of that point is going to be the line x minus 2. Again, if you're not sure what the slope, you could, if you want, go ahead and plug in negative 2. Plug in negative 3. Plug in negative 4. And get those y values. There's nothing wrong with that. But I know this is just a slope of 1. So I'm just going to draw my line. All right, then on my next one, let's take negative 1, plug it in. The absolute value of negative 1 is 1. Negative, though, then we make it negative. Negative 1 plus 3 is 2. So this goes from negative 1 to. Again, it depends if you're familiar with a parent function or if you want to just continue to plug in points. If you want to plug in 0, 1, and 2, you can. But I know this is an absolute value function. It's shifted up 3. That means my vertex is here. It's going down because of the negative. And then I know at 2, I'm going to have an open circle. Then my last one, plug in 2. Okay, 2 minus 1 squared, that's 1 minus 2, negative 1. That's going to be a filled in circle because it's or equal to. And again, at this point, you can either plug in 3 and plug in 4, or you could think, hey, this graph has shifted right 1 and down 2. So normally that's my vertex. Well, if that's normally my vertex, then I would normally go right 2 and up 1, 2, 3, 4. And right 3 up 9. Or again, if you want, you can just plug in 3, either way. All right, a couple more examples. So when x is less than negative 3, I'm graphing the line y equals 5. That is just a horizontal line. So at negative 3, I've got an open circle. And just a horizontal line coming off of it. And that was not a very good horizontal line. Then in between negative 3 and 2, I have the parabola x squared minus 4. So again, I could plug in negative 3, all right? Then I would get 5, which you'll notice is already a point on my graph. So that open circle is now getting filled in with that closed circle. If I plug in 2, 2 squared minus 4, 4 minus 4 is 0, so 2, 0 is on that graph. Then in between those points, it's going to be a parabola that's shifted down 4. So there's my vertex, and I forgot that should have been an open circle. And let me get a couple more points to make this a little bit prettier. Sorry about that. Right 1, up 1, left 2, up 4. There we go. Get a little bit of a nicer parabola in the middle. All right, then my last graph, square root function that's shifted right 2. So square root function that's right 2. If I plug in 2, I'm going to get 0. So that circle is again filled in. So then from this point, I normally go right 1 and up 1, left 4 and up 2, or right 4 and up 2. Or again, you could just plug in points if you want. So what you'll notice now, this graph is actually continuous. So this entire function, even though it's piecewise, is still continuous. Whereas those previous graphs, apologize, I forgot to put that on there. These previous graphs did have discontinuities. They were all jump or break discontinuities. So this first graph was discontinuous at x equals -2. And then this graph was discontinuous at -1 and also at 2. And again, it was either a jump or a break. But again, C was not discontinuous at all. All right, so the last one that we're going to look at, a little bit different. This one doesn't say less than or greater than. This one says equal or not equal. So it is still piecewise. Okay, we do still have different pieces of functions. This first one is graphing this graph right here everywhere except for 1 point. Well, let's go ahead and see what this graph looks like. It looks like it's rational, but if I factor this, we're going to realize it's not going to look very rational. If x minus 2 cancels out, that means I'm going to have a removable discontinuity. That removable discontinuity is going to happen when x equals 2. If I plug in 2, I would get the y value, which is 4. So 2, 4 is an open circle on my graph. Everything else that remains is just the line x plus 2. Now what's nice about this, that corresponds really well to what you're given for the piecewise functions. It says it's that function everywhere except when x is not equal to 2. Well, we've already concluded that. We have a hole there. What this graph does tell us, though, is because when x does equal 2, y is equal to 3. So that means 2, 3 is a point on this graph. So what we have is a line with a hole and then another filled in point. So while this graph is defined everywhere, it's not continuous because of that hole. Now, what's interesting, though, is if this value were different, let's say if instead of 3, this was 4, that graph would be continuous because it would fill in the hole. But in this case, it doesn't. And again, what makes that different than those graphs we looked at previously, like the ones that did this, even if I fill in that hole, that graph still is not continuous. Removable discontinuities are a little bit special in that way, though. All right, so the last thing we're going to do is we're going to go backwards and just write the equation. And this, again, is just really good practice for just writing equations of graphs. So what we have to do in order to write these equations is we basically write the equation of each piece, and we write the domain that goes with it. So looking at this first one, the equation of that line is f of x equals 3. Then we write the domain that goes with it. X is less than -1. In the middle, we have a parabola. It's shifted up 1. It has not been stretched or compressed in any way. It has not been reflected. We write our domain. Because -1 has a filled in circle, that's going to be or equal to. Then we look at our last piece. All right, we know the slope. To see the y-intercept, we can either solve algebraically or we can just continue the graph. So this is a -x plus 4. The domain is when x is greater than or equal to 2. Then on the last one, same concept. Start with the first graph. That's a square root function. It's been reflected over the y, though, and it's shifted up 2. It has not been stretched or compressed because it follows that same parent function pattern. From your starting point, you went up 1 over 1, and up 1, 2, 3, 4 over 2. And it's a little bit cut off, but you can see it's about to touch that point. That's happening when x is less than 0. In between there, we've got a quadratic. The domain that goes with it, sorry, let me write the actual quadratic. It's shifted right 2 and down 3. Has not been stretched or compressed, still follows the same parent function pattern. Domain that goes with it, it's between 0 and 3. But again, at 3 and at 0, those are both defined points. So those are both going to be or equal to. Then the last point, y value, it's just y equals -1. That's it, horizontal line. The domain that goes with it is x greater than 3. All right, so that's it for piecewise functions. Again, this is something you've seen this year, really just kind of throwing in some of the older or the newer graphs that we've done to really just kind of get some of that reviewed. Very similar to what we did last class. So again, you got a couple practice problems. The Desmos activity is going to be the check grade this time. Again, if you have questions, you can email me or fill out that video request. Again, on that video request, this one should be Thursday by 4 p.m. and I'll get that up for you guys.